So we're going to calculate the expected value. And that calculation is done by this formula, x times p of x. Let's do that for rolling some dice. So here's your x in this column. Here's your p of x in this column. So what do we start out all our Google Sheets commands with? What do they always start with? Equals. So we're going to do equals and then click this one, the 2 in row 33, column A. And then you need to hit the times, which is shift 8. And then this one. So that's your x times p of x. Now when you do that, chances are it'll offer you the opportunity to copy that formula all the way down. You can just click yeah. Like, yeah, you want to do my work for me? No problem. Now, I don't know if it'll do that for me or not. Yeah, it does. So you just click the autofill. Sure. Do it all the way down to the bottom of the table like that. And then down here, you want the sum of these values. So if I click this, it's kind of nice. It'll highlight. That's all the values I'm summing up. So what does that tell me? It tells me, on average, when you roll a pair of dice, your average roll is going to be a 7. Now, does that mean that the next time I pick up a pair of dice and throw it, I'm going to get a 7? No. What does it mean? What is the average being a 7 tell me then? Anyone home? It could be a 5 and a 2, or a 2 and a 5, or a 6 and a 1. So it could be a lot of different things, but what it means is that if I did this experiment hundreds of times, if I was rolling a dice all night long, and I added up all those rolls and divided by the number of my rolls, on average I should get something close to a 7. That's my average roll. If you repeat this experiment often and often enough, you're going to get an average roll of 7. Nice. Now, there was something else that we did in association with this. That was, we found the mean and standard deviation. So let's find the standard deviation part. Standard deviation is going to come in a couple different steps. And you know what? I'm just going to erase these things here because I want to do them from scratch. And maybe you wanted to follow suit. So erase the variance and the standard deviation so that you can practice calculating those two. I mean, if you don't, it's not a big deal. All right. So for the variance, and the variance is one of the things that we have to look at how spread out things are. The variance, you want to do this calculation. P of x times x minus mu squared. All right, so there's a lot going on with that one. Let's carefully do this one together. Now, if you haven't already, go underneath the File menu and click Make a Copy. Save this someplace that you can get at it when you want to reference it in the future. Equals. Well, where's P of x? Where should I click to get P of x? What column? C. Times. You need to hit that times key. And then in parentheses, x. Well, where's x? Yep, that's in column A. So I'll click there, and there's an A33 minus the mu. Now, I'm not going to explain why. But when you do this formula, just this one, actually write in the number mu. Don't cheat on this one and click a different cell. You want to write in the mu. So minus 7, right parenthesis, then the square key, you can do shift 6 to get that little up arrow caret, and then a squared like that. So I'll leave that there for a second so you can see that formula. So interesting enough, not only is 7 the most likely outcome, because if you look at the probabilities of 1 in 6 out of 36 or 1 in 6 chance you get a 7, but it's the average outcome. Those are different things. They don't always have to be the same. They are in this case. So if I hit enter, let me come back here. Let's enter. Do you want to autofill? Yeah, sure. Now, if something goes wrong and yours doesn't autofill, remember you can click and drag this all the way down. So either way, you should be in good shape. Now, the sum of this column is the variance. So let's put that here. The variance is sigma squared. That's the sum of P of x times x minus mu squared. That's what we just calculated. So notice that there's that Greek letter sigma there. What does that Greek letter sigma mean to you? Sum. It means you need to add it all up. So let's do that. Come back over to here. I need to add all these up. Now I'm going to be a little bit lazy. I don't want to type in that command. Gee, it's so much I have to sum it up. But you know what? I typed that in that command over here. So I'm just going to drag this over to the right. And bam, I get the sum. So it's just a faster way. And you don't have to do it. It's just kind of a nice little shortcut there. So let me pause here for a second. Are we doing okay on finding the variance? My homies, you guys okay? Thank you. All right. Thank you, Michael. Thank you, Z. Now for the standard deviation, let's see. Let's go back to here. For the standard deviation, does anyone know how to calculate the standard deviation once I have the variance? Yeah, the square root of all of that. So all I need to do is I need to take the square root of this now. And let's do that. Now to get the square root, I'll type equals SQRT. That gives me the square root. Left parenthesis. And then click the cell right up above it. And you should get 2.41 for the standard deviation. Yay! Is everyone able to get that value there?
Wait, how did you do that?
Let me highlight that formula. It's right up here. Square root of the above cell. Good? All right. Thank you, Dave. Thank you, Michael. All right. Looking good. Let's do a little bit more with that. You might remember earlier on in the course when we used standard deviation, we used it to help identify what was typical and what was not typical, right? How far away from the mean did we go to set that boundary of what was typical and what's not typical? 2 standard deviations, right? So let's take the mean and go 2 standard deviations below it and 2 standard deviations above it and see what happens. And see if we can't find out what's typical. So that's up here, and I guess I've already got that calculation in there for us. So lucky you. But the mean, that's our 7, minus 2 times the standard deviation. And then there's our mean plus 2 times the standard deviation. So let's take a look at that for rolling a pair of dice. And try and understand what that means. Two, 3, 4, 5. So here's all the different things that can happen when you roll a pair of dice. And what we found out was we got ourselves a little cut points, a little range of values to cut off what's typical and what's not typical. So let's see that. And what was typical goes all the way down to 2.16. So let me put a little mark there. We'll call it 2.17. And then on the top end, 11.83. So something like this. So these are our typical values. Or maybe I just should say that they're not significantly high and not significantly low. Now, does this include the 2? If I rolled a 2, is that unusually low? Yeah, 2 is unusually low. That's not in this range. Now, can I actually roll a 2.17? No, not with a pair of dice. No, not the times we use. Nor can I roll 11.83. That's okay. It still sets the boundary. Basically, it sets the boundary for us right here, between 3 and 11. Those are your usual rolls. Whereas here at 2 and here at 12, those are significantly high and significantly low. Significantly high and significantly low. So those would be unusual values, and that's true. There's only a 1 in 36 chance you could roll either of those. Nice. Nice. How are we doing on our first example here? Doing okay with that one? Were you able to keep up with the calculations? This is something I expect of you, that you can calculate the mean and standard deviation of a distribution. And we'll probably end up applying it to, problems like this too, where you're asking what's significantly high, what's significantly low, based on 2 standard deviations away from the mean. Okay. Let's see if we got a couple more here that we can look at. Let's follow up on our previous calculation by sticking with expected value. Now, the expected value is what you expect to happen on average. If you do this experiment again and again and again, it's what's going to happen on average. It might not be something that could actually happen in the experiment. Like this one. Says, when playing roulette at a casino, a gambler is trying to decide whether to bet $10 on the number 35 or to bet $10 that the outcome is any of these 3 numbers: 00, 0, or 1. The gambler knows that the expected value of a $10 bet is negative $1.06. For the bet that the outcome is 0001, the probability of making that is 3 out of 38. And if you did hit that, they'd pay you $30. So, okay. Now, that means you have a 35 out of 38 chance of losing $10. Let's figure out its expected value. So I'll call this example D, just to keep up with the way I've labeled it here. Example D. There are 2 things that can happen when you're doing this game. So I'll call those X, and we'll look at P of X. You could lose $10. Or you could win. Did anyone catch how much it was? How much could you win if you win that particular bet? $30. Nice. Now the probability of winning is just those 3 numbers out of the 38 that are available. So 3 out of 38. If that's the probability of winning, what's the probability of losing? Or how would I find the probability of losing? Subtract 3 over 38 from what number? From 1. So it'd be 35 out of 38. That's your chance of losing. Now, let's extend this table a little bit further. Remember to calculate the mean you're going to calculate x times p of x. Now, if you wanted to do this on Google Sheets or on your calculator, that's fine. Doesn't matter. We're going to do this times this, this times this. And let's calculate the expected value here. So let's see. That'd be negative 10 times 35 over 38. Now you might want to write that as negative 10 over 1. Do you remember how to multiply fractions? Do we need a common denominator to multiply fractions? No. So it's going to give me negative 350 over 38. And likewise down here for the denominator, I'll end up with 30 times 3 over 38. Basically 90 over 38. So there's my column of x times p of x. What do I have to do in order to find the expected value? Because this isn't the expected value yet. What do I have to do to find the expected value? What did I do in the last example?
You have to take the sum of them.
Yeah, you have to add it up, right? All right. Now there's something nice about adding these things up. Does anyone know what it is? Yeah, they have a common denominator. So it's just adding up the numerators. So negative 260 over, it should be 38, not 380. Let's take care of that. A little Photoshop. There you go. Never happened. 38. And that should be a little bit over, it's just 6 something. So let's see here. 260 divided by 38. Yes, 684. Now I'm just rounding this to the nearest dollar or the nearest penny because we don't have anything smaller than that in your unit of currency. So there you go. That's the expected value when you're playing this game. I've got 2 questions for you in regards to this. The first one is, what does the negative reflect? What do you think that negative in all this means? I need one at a time. Go ahead. Yeah. It says you should expect to lose money. You're gambling, right? Big shocker. The odds are stacked against you. If they weren't, Vegas couldn't exist to be around. All right? They wouldn't have money to pay their employees or their light bills or anything else. Yeah, spot on, Dave. You're going to lose money. Now, that's the expected value for this bet. The expected value for the other bet, if you're just betting one number comes up, then your expected value is negative 1.06. Which one, if you were smart, which one would you be better off playing? Yeah, the one number. Because its expected value isn't as bad. Here, on average, you're going to lose $6.84 every time you gamble. Now, can you lose $6.84? No. You're either going to lose 10 or win 30. But at the end of the night, if you're betting hundreds of times, you're on average going to be losing $6.84 a throw. Whereas here, it's only $1.06. That's a big difference. Now, let's drive that point home a little bit more. Here's your state's Keno game. This is the state of Michigan. So let me put up this here for us. There you go, Keno in Michigan. You can pick how many spots you want to match. Basically, there's 80 numbers. And you can pick how many spots you want to match, how much you want to bet, etc. And And you can play, you know, the 1 spot all the way up to the 10 spot. Great. I've gone through and calculated the expected value of some of these games. And let's see, that's right here. Now I think there's a link in this, in section 5.1. I think there should be a link to this Google Sheet. So if you follow that link, here we go. Up here near the top, there we go. Here's the expected value of the different games. Which game would you play? The 4 spot, 5 spot, 6 spot, 7 spot, 8 spot. Which game do you want to play? I got to vote for this 4 spot. Somebody in my morning class said the 5 spot. Who's right? 4 spot or the 5 spot? Do you want to play the 4 because it's the smallest? You want to pick the 5 because it's the largest? Yeah. Yeah, I want to play the 4 spot. Thank you, Dylan and Arian and Dave. Yeah, thank you. Thank you one and all. So, yeah, now if these were positive numbers, then I'd want the biggest one. But since they're negative numbers, I want the smallest one. I want the odds stacked against me as least as possible. I mean, look at this. The difference between the 5 spot and the 4 spot is enormous. I mean, you're going to tear through your money big time playing the 5 spot. I had somebody in my morning classes say, I work at a restaurant, and there's times I see people spending the whole night and not winning a single dime on the Keno. I mean, not that I want to convince you to or not to, but I guess the thing that I do want to wake you up to is that it makes a difference where you put your money. Because, I mean, some of them are bad bets and some of them are good bets. I mean, if you're going to bet, and if I was going to bet this, it'd be the 4 spot all day. All right? That's just a clear choice. What strikes me odd is just how much they vary, you know? But the 4 spot's the best one. Yeah, so to put that in perspective, that means every time you wager $1, on average, you could expect to lose 9 cents. So if you bought 1,000 tickets, 1,000 times 9 cents, you'd be losing what? $9 on average. So that's what you would expect. Now, would you lose exactly that much? No. That's just on average what you would expect to lose. But boy, if you're betting the 5 spot, you're betting $1,000, on average you're going to lose about $712, $713. Wow. Huge difference. Okay, let's keep going. Actually, you know what? I think if you times this by 1,000, you'd be losing on average $91, not $9. Sorry about that. Are you comfortable with calculating expected value and what it means? Can you calculate the mean and standard deviation? All right. Those are things that I expect from you from this section, is to be able to do those too. So if there's any question, now's a good time to get an answer. Of expected value and mean and standard deviation. Let me see what I've got here. Be helpful if we let's see here. All right, so let's take this one. Let's see, did we do this one last time? Yeah, that was number of sleepwalkers. All right, let's take this one. And this is kind of a nice setup for stuff we're going to do in the next section anyways. And if you go all the way at the top, it says number of girls amongst 10 babies. Let's clean this up. Let's clear that out because I want to redo that calculation. I want to do this whole thing from scratch. So this column for C, from C3 to C13, just highlight that and hit the delete key. It should clear everything out for us. All right. So I want to go back and calculate the mean and standard deviation. I'm also going to clear out these two values, this one and this one. Let's clean out those. So, kind of like before, we're going to do x times p of x. How do our Google Sheets commands start out with? Equals, thank you. So equals x star p of x. All right. And then for me, it didn't offer me the chance to, let's just copy those all the way down. So I'm going to click this little box here and drag it down as far as I need, which is down to row 13. And it adds everything up. And oh, look, that's kind of cool. The expected value is 5. So on average, if you looked at lots of different hospitals and looked at babies in groups of 10 and asked how many girls there were, the average number you're going to get is 5, which is what you expected anyways, right? Now what you're going to see in section 5.2 is that there's a shortcut to getting that value. But that shortcut only applies to particular types of random variables called binomial random variables. Now, here's the hard part. And maybe I should have put a little star or an asterisk between these things, because if you don't have that asterisk, I think it might not like it in your formula. So let's see, equals p of x. Well, that's in column B. Asterisk, so times x, that's in column A, minus mu. Now for mu, I gave you some advice. Who remembers that? What was the advice I gave you when working with mu? Yeah, actually type in the number for mu here in this formula. So that number was 5 raised to the second power, like that. So I'll leave that formula up there for a moment for you to catch up to it. So B3 times left parenthesis A3 minus 5, right parenthesis squared. And for that first one, it gave me 0.0244. And mercifully, it's asking if I want to autofill. Yeah, every day, all day. Let's autofill that. Now for my variance, I want to sum up all those values. I'm just going to steal this calculation over here again, right? I mean, I've already got the sum here, so I'm just going to drag that over to here. Oh, and I got 2.5 for the variance. Nice. Yeah, please.
What exactly does the variance tell us, or is that just like a
The variance
how to
is
get to the standard?
it's one step on the to get to the standard deviation. It still does express how much variability there is. The problem with interpreting the variance is that it's not in the same units as the standard deviation or as the original problem. So whereas in the units is number of girls, and that'd be the expected value here, variance is numbers of girls squared, which is a unit that I can't really make sense out of for you guys. I mean, girl squared, I mean, I don't know. Hard to make sense of what that might be. Now, how do I get the standard deviation once I've got the variance? Square root. So equals SQRT. And then just click the number above it. So square root of that, 1.5811. How many of you people were able to get that? Let me see some hands. All right. Some of my homies able to get that one. All right. Thank you, Dave, Michael, Ashlyn. Good. Good. All right. I appreciate that. All right. And one more here coming up. Yulia. All right. Spasiba. Good deal. Are you comfortable with those things? Finding mean and standard deviation? If you did your mu minus 2 sigma and mu plus 2 sigma calculations, let's see what that would give us. So equals mu was 5 minus 2 times sigma. Now for sigma, I'm just going to go down here and click that. So 5 minus 2 times the cell that I have in D15. So that's mu minus 2 sigma. And up here equals mu plus 2 times sigma. So given this, what values would be unusual? If you were looking at 10 babies in a hospital, look at the number of girls, what values would be unusual? Would 2 be an unusual value? Not 2. What about 1? What about 0? 1 and 0 would both be unusual. Are there any other unusual values? 9 and 10. Yeah. So anything outside this range. Now, obviously, you can't have 1.83 baby girls, but it still just gives you a cutoff. And what that cutoff doesn't include are values of 0 and 1. And on the other side, 8 doesn't include 9 or 10. So those would be the atypical values there. Okay. Good deal. All right. Anything else on this one? Okay. Let's call it a day on this section. Move on to section 5.2.